Hey, what's up, you guys? So, in our previous videos, we covered questions 1 through 9, and in this video, we'll proceed with the last question of section 4.1, which is number 10. So, this one right here. Now, before diving into the solution, let's start with our written review of the steps to approach the problem. So our first step is to substitute power series representation, y prime, and y double prime into our main differential equation. Our second step is to match the exponents or the powers of x to n. So we need to make sure that all the x's of the multiple power series that we have, they all have the power of n. And then our third step would be shifting the indices of all the power series we have. Okay, and remember the third step comes after the second step, so we will try to shift them after we transformed them so that their powers or their exponents have been transformed to n. Okay, and then like I said earlier, we will always keep the larger index, so the power series that has the largest index will stay as it is, and we will try to shift the indexes of the power series which has a smaller value. So the smaller value starting index power series, they get shifted. Okay, and then we have our fourth step, which is combining the series to one. So after we have performed our second step, that is making sure that all the powers of the power series has the power n, and also all the indices of the power series start from the same index, then now we can combine them into one. And after performing the fourth step, now we will find the coefficients, okay, and we use our recurrence relationship in order to do that. And then right after determining the coefficients, we can finally find the general solution. In this form, I've constantly applied these steps to every problem I've solved, so all the problems in section 4.1 follow the same approach. So without further ado, let's dive into the problem. So in today's problem, we have y double prime plus x times y prime equals 1 minus e to the power x. Okay, so now doing our first step, which was substituting our y's with our power series representation. So we know that we have our y, which is summation n equal to 0 to infinity a sub n times x to the power n. And we already know that falls under our red box. And then we have our y prime, which is summation n equal to 1 to infinity a sub n times x to the power n minus 1, which is our green box. And then I have my y double prime, which is summation n equals to 2 to infinity a sub n times n minus 1 times x to the power n minus 2, which is going to be our blue box. So in our main differential equation, well, we don't have y today, so we're just going to plug in my y prime and my y double prime. Now, at our right, we have something new. We have a new guest, e to the power x. And in previous videos, there was one question where we had to deal with cos x, and we learned about the new power series for cos x. Here we will also use a different power series for e to the power x, which is basically summation n equal to 0 to infinity x to the power n divided by n factorial. I will use a purple color for this new guest. Okay, so our new guest gets a purple color. Okay, so now plugging in our power series into our main differential equation. So I have summation n equal to 2 to infinity a sub n times n minus 1 x to the power n minus 2. And then I have a plus and then an x, and then I have my y prime, which is summation n equal to 1 to infinity a sub n times x to the power n minus 1 in a bracket. And then I have 1 minus e to the power x. And I know that my e to the power x has the power series of this form. So I'm going to use my color marker again. So I have summation n equal to 0 to infinity x to the power n by n factorial. Okay. And then I'm going to distribute my x, okay, with my second power series. So I will have summation n equal to 2 to infinity a sub n times n minus 1 x to the power n minus 2, then plus, then summation n equal to 1 to infinity a sub n times x to the power n. Again, by rules of exponents, I know that if the bases are the same, that means their exponents add up, their powers add up. So in one of my x has n minus 1, the other one has just 1. So if I add them up, I'm left with x to the power n. And then I have my 1 minus this beautiful guest, summation n equal to 0 to infinity x to the power n times n factorial. Now, this is what it looks like when we plug in our power series into our main differential equation, okay? Now, our second step was to match the exponents to x to the power n. So these powers needs to be just n. And I can see that my second power series already has an n. That means the second one doesn't really need to have any sort of transformation. So all I need to transform my first power series, okay? So let's go ahead and do that. So I have my first power series, which is n equal to 2 to infinity a sub n times n minus 1 x to the power n minus 2. And this gets transformed. Then I have this blue color, summation, and it gets transformed to just an n. Okay, and if I look closely or carefully, that if I just add 2 to it, then my negative 2 and my positive 2 gets cancelled. So I'm just left with n. So all I need to do is add 2 to all my n's. That means my a sub n now becomes a sub n plus 2. And then my n over here becomes n plus 2. And then my n minus 1 becomes n plus 1. Okay, because n minus 1 plus 2 is just n plus 1. And since all my n's increased by 2, that means my starting index will decrease by 2. So instead of starting from 2, it's now going to start from 0 to infinity. Okay, so this is what my first transformed power series look like. So we can go ahead and write that. 0 to infinity, a sub n plus 2 times n plus 2 times n plus 1 x to the power n. And then I have my second power series, which is as it is, which is not transformed since they have the power n already. And then on the right-hand side, now what I'm going to do is I am going to expand this power series, which basically means writing out the terms for different values of n, starting from n equal to 0. Okay, so I have, let me use that same color. Oops, okay. So when n is equal to 0, so I have x to the power 0 and then divide by 0 factorial, which is just 1. And then plus, and then when n is equal to 1, so I have x to the power 1 and then divide by 1 factorial, which is just x. And then when I have n is equal to 2, then I have x squared, divide by 2 factorial. Okay. And then when I have my n equal to 3, I have x to the power 3 and then 3 factorial, and so on. Okay, so this is what it looks like when I expand them. And I can see that there's basically coefficients for all powers of x. Okay, all right. So again, if I take out the brackets, okay, then I can see that my positive 1 and my negative 1 gets canceled, okay, and all my signs now just becomes negative. So I'm going to write that over here. Just note that all my negatives all my signs are just negatives now. All my coefficients are just negatives now. Okay, and so on. All right, so the good news is that there is a coefficient for all powers of x, okay? And just by looking at it, I can already see that there is no constants. The constants I had canceled out each other, okay? So all I have are just coefficients for different powers of x. So amazing. Okay, so I have done my second step, which was making sure that these exponents are n. Now I have to make sure that my starting index is also the same. Okay, again, I can see one of the starting index is a 0, the other one is a 1. And again, by, conventionally, we always shift the indices with the smaller starting index to match the one with the larger starting index. So I can see that my n is equal to 1 is the larger one, so I'm going to shift my first power series, okay? And in order to do that, I have to write my n is equal to 0 terms separately, okay? So when n is equal to 0, this thing becomes a sub 0 plus 2 times 0 plus 2 times 0 plus 1 x to the power of 0, which is just 2a sub 2, okay? So let's write that. And then now that I have written my n is equal to 0 separately, I can now shift my indices. I can start my index from 1 now, okay? So let's go ahead and do that. So I have summation n equal to 1 to infinity a sub n plus 2 times n plus 2 times n plus 1 x to the power n. And then I have my plus, then summation n equal to 1 to infinity a sub n times x to the power n. And then I have whatever I have at my right. Okay, I'm not just writing this for now because we already know that this is what's going to be at our right hand side. Okay, all right, so I can see that my exponents match. Right now they have the power n, and they also have the same starting index, which means that now I can combine them into one. So when I do that, I have summation n equal to 1 to infinity x to the power n. So just writing out the leftover terms. So I have a sub n plus 2 times n plus 2 times n plus 1, then plus a sub n times n equals the same thing. Okay, I'm just being lazy today. Okay, I'm not very proud of it, but I'm just being lazy today for some reason. Okay. So now we have also successfully performed our fourth step, which was combining all our power series to 1. Now this is our fifth step, which was solving for coefficients. So now we need to know what our coefficients are, okay? So I have my a sub 2 and then all my a's, okay? So I want to know what these values are. Okay, now in order to find our coefficients, we use our recurrence relationship. So first, I'm going to look at my constants if I have any, and I can see I do have a constant, 2a sub 2. And if I look at my right, like I've seen before, that we have coefficients for different powers of x. We don't have any constant. So that means my 2a sub 2 goes to 0, which means my a sub 2 is 0. Okay, now I already have my a sub 2. That means I have my a sub 0 and a sub 1, and I'm not given any initial values. So I know that it will be arbitrary numbers. And since this is my second order differential equation, that means I have two arbitrary numbers. And again, conventionally, I always take my a sub 0 and my a sub 1 as my arbitrary numbers. Okay. Now I have to generate 5 terms. That means I need more coefficients. So now for that, I'm going to use this beautiful power series I have got. Okay. And in order to find the coefficients, I will try to look for the corresponding coefficient for different powers of x at my right. Okay. So let's go and do that. So when n is equal to 1, then the power of x is 1, and I have a sub 1 plus 2 times 1 plus 2 times 1 plus 1 plus a sub 1. And if I look at my right, I can see that it's negative 1x, okay? I didn't have to write negative 1, the 1, I could have just said negative x. Just wrote that just for you guys to see. Okay, so if I simplify that, I have 2 plus 1, which is 3, and then 1 plus 1, which is 2. So 3 times 2 is 6. And then I have my a sub 3 plus a sub 1, which is negative 1x. And, x and x cancels out. So I have 6. A sub 3 plus a sub 1 equals negative 1. I already know that my a sub 1 is an arbitrary number. So my a sub 3 is negative 1 minus negative a sub 1. Then taking out the 6, I have negative 1 by 6 minus negative 1 by 6 a sub 1. And this is my a sub 3. Now, when n is equal to 2, I have x squared, a sub 2 plus 2 times 2 plus 2 times 2 plus 1 plus 2a sub 2. Okay? And if I look at my what I've got at my right for x squared, I can see that I have negative 1 by 2 factorial, which is basically a negative 1 by 2 because 2 factorial is just 2. Okay, so I have negative 1 by 2 x squared. Now canceling out my x squares and then simplifying this, I have 2 plus 2, which is 4, and 2 plus 1, which is 3, and 4 times 3 is 12, and a sub 4 plus 2a sub 2 equals negative half. And I know that my a sub 2 is 0, so that means I have my a sub 4, just half by 12, which is negative 1 by 24. And that is my a sub 4. Okay. Let's find for a sub 5. So when n is equal to 3, I have x cubed by a sub 3 plus 2 times 3 plus 2 times 3 plus 1 plus 3a sub 3. And then if I look what I have at my right, I have negative 1 by 3 factorial, which is negative 1 by 6. Okay. So I have negative 1 by 6 x cubed. And the x cubes cancels out. I have 3 plus 2, which is 5, and 3 plus 1, which is 4. So 5 times 4 is 20. And then I have a sub 5. And then I have 3 a sub 3. And if I look, that my a sub 3 is negative 1 by 6 minus 1 by 6 a sub 1. So just plugging in that value, I have negative 1 by 6 minus 1 by 6 a sub 1 equals negative 1 by 6. Now, simplifying them, I have 1 by 2, negative 1 by 2, and then negative 1 by 2 a sub 1 equals negative 1 by 6. And then again, if I substitute, if I just simplify all that value and also making sure that my a sub 1 is an arbitrary number. So I have my a sub 5, which is 1 by 60 plus 1 by 40 a sub 1. And that is my a sub 5. Okay, so now I have 5 coefficients for my 5 terms. All right, so now I can write the general solution. So I have my a sub 0, which is an arbitrary number, plus I have my a sub 1, which is also an arbitrary number, and then my a sub 2 is 0, x squared, and then I have my a sub 3, which is negative 1 by 6 minus 1 by 6 a sub 1, x to the power 3. And then I have my a sub 4, which is negative 1 by 24, x to the power 4. And then I have my a sub 5, which is 1 by 60 plus 1 by 40 a sub 1 x to the power 5, and then so on. Now, you can keep this answer as it is, okay? This could be your final solution. But again, if you want to simplify, if you want to rearrange these values, and if you have a better way of simplifying these values, a more interesting way, you could do that as well. So I'm going to do like a more interesting way of simplifying it for those curious cats out there. Now, if you look for my 6 in this term right here for x cubed, this is the same thing as, 3 factorial. Because 3 factorial is 1 times 2 times 3, which is 6, okay? Now, if you look at 24 right here, this is basically 4 factorial. Since 4 factorial is 1 equals 1 times 2 times 3 times 4, which is 24, okay? Now, if you look over here, you'd see that, okay, now there are different numbers, right? They have different factorials. But if I try to find their LCM, right? So if I want to find their LCM, I have 2 times 2 times 5 times 3 times 2. And if you do the multiplication, so I have 2 times 2, which is 4, and then 4 times 5, which is 20, and then 20 times 3, that is 60, and then 60 times 2, that is 120, okay? And if you look closely, my 120 is basically 5 factorial, okay? Since 1 times 2 times 3 times 4 times 5. Okay, if you look right here, 5, and then 3 and 2, and then 4. Okay, so that's basically my 120. So I can see that my solution can also be written as factorial in factorial terms, okay? Again, this is completely optional. All right, you don't have to think deep about it, okay? If you don't want to keep that as factorials, it's completely fine, okay? All right, so I can see that with whatever terms I have, I can write them as factorial, right? So why can't we just go ahead and write them in factorials, right? So just simplifying them further, I have a sub 0 plus a sub 1x, and then I can write minus 1 by 3 factorial. Then I have 1 plus a sub 1 x cubed. And then I have my minus, minus 1 factorial, 4 factorial, x to the power 4. And then I have my plus 1 by 5 factorial, which is 120. And then 2 plus 3 a sub 1, x to the power 5, and then so on. Okay, so this is another type of solution where you want to write them on the basis of factorial. This is completely optional. Okay, you don't have to write that. You don't have to, if you don't have much time, you're running out of time, you're running late, you don't have to do all of this. You can just write the solution as it is, okay? All right, we have now completed all 10 problems in section 4.1 focused on solving differential equations using the power series approach. I hope working through these problems has been very helpful for everyone. And in my next video, I'll be back with a new section and another journey into solving differential equations. Till then, take care everyone and keep practicing, and I will see you in my next video. Bye.